everyone. Hope you had an amazing DevCon experience so far. Let's just start it with. Do we have something? Oh, there we go. Just go back. My name is Kasra. I am one of the core builders and contributors of eRPC, which is an EVM, which is one of the basically like a EVM RPC proxy tool. eRPC has been used in production by a lot of important Web3 projects, including Circle, Euler, Moonwell, Morpho, even ETH Ops team is using it. So we are really lucky to get the feedback and users from all these teams. The main topic of this talk is basically like solving EVM RPC reliability issues. But it's important to take a step back and understand, in a really simplified way, how does the EVM RPC stack looks like and what are, let's say, the common failure points. For any Web3 team that wants to start building something on blockchain, even a small team or a big team, there's a really important caveat compared to, let's say, Web2 world. From day one, you might need to handle terabytes of data. If you're on like multi-chain and all those things, just the sheer volume of data that you need to handle is just a lot. And just compare that to like a Web2 company, right? You don't start with terabytes of data from day one. You might have some external data that you kind of start with, but it's not like production critical data that you need to handle. So that kind of brings like the importance of like, we have a really kind of important job on our hand to make sure that data is being handled properly. And that kind of brings us to the point of RPCs, because JSON RPC is kind of awesome. So it kind of tries to be a standard for us asking blockchain about data. So just take like different use cases on blockchain. We have DeFi's, they allow you to do stuff. Indexer just get the data from blockchain and process it and put it somewhere. Front end shows something to the user. And each one of these kind of use cases send different RPC methods. Give me all the events like get logs or give me traces, debugs, all those things. But the way it works is like each one of those kind of use cases send the RPC method to the upstream level, which we call, let's say, our bespoke RPC providers. You might have like, say, your enterprise RPC providers, public nodes. You can even self-host it yourself. But inherently, because each one of those, let's say, nodes have multiple, like, say, infra layers, like we have seen the Cloudflare like outage like 2 days ago. We know about AWS, and each one of those providers are working with, let's say, different clients and all those things. So we just have a magnitude of like different failure points. So I'm pretty sure all of you have faced issues as also the previous talk as well, that different clients just give you like different results for get logs, for example, or your app is in US East and the RPC provider is in Europe. There's just like added latency. There's timeouts, there's issues, all sorts of things. And the users kind of don't care about any of this. They just want to lend, borrow. They don't want to kind of see the wrong results or have issues. So it's kind of our job to kind of solve those problems. And very briefly, like each one of those providers are working with different clients, amazing people from all those teams here. But again, because also in this layer we have DevOps related, we have code logic related, different versions could have different issues. We actually had an issue about 1 month ago that like one of the clients just were like processing the log index incorrectly, and that kind of the downstream effect of it was the user was getting some sort of a negative balance on their app. So again, inherently we have different reliability challenges in this layer. And that's where kind of eRPC comes in. eRPC is, oh wow, this slide has gone really bad, but I think you get the point here. That's where eRPC comes in, because eRPC is kind of a captain or like a top middleware layer that sits on top of your RPC stack. And if you're a small app, you might have only one node, but as we know, like any production company, you need to be on multiple chains. You have different nodes, you have different clients. So just your RPC stacks becomes like complicated, definitely. So eRPC helps you kind of, in short, it wants to send every single RPC request to the best node possible. And we give you all the knobs possible to kind of, configure based on your environment. Sometimes you want to increase reliability, right? Sometimes you want to increase data quality. Sometimes you want to reduce latency or reduce your cost. So you can think of eRPC basically as like, it's a load balancer, it's a caching tool, it's a data validator, it's a failover system. So for example, if one of your nodes is down, no problem, eRPC just handles it through automatic failover. Or what if one of my nodes is slow? Okay, eRPC has hedge mechanism. It just sends multiple parallel requests to the nodes, and the first response we get, we're going to accept that, and we're going to cancel all the others. What if the nodes disagree on a result? Okay, we have consensus policy. We just send the request to multiple nodes, and if 3 out of 4 agree on a result, we're going to accept it. So just like increase the resiliency and reliability of your RPC stack. You can just sleep better at night. And also in the past year, I have probably talked to hundreds of teams, and it's really funny that a lot of teams just build something in-house for this. And you might ask, okay, why don't I just use a traditional LB solution, like Envoy or Nginx or something? And the point is, like, none of those tools have EVM context, right? You just don't want to, you don't have like a simple health check, like is the node is up or down. You might want to have like the latest block height tracking, like how far away is behind the tip of the chain, or I want these nodes to kind of handle these methods because I know that they're optimized for it, but like I don't know, maybe traces needs to go to this method because So it's just like EVM knowledge about finality, about different methods, about different chains, block height, like all these things basically is baked into the eRPC, different normalization of errors, so you can just basically again route every single RPC request to the best node possible. Now I think it's a really good time to walk through some production examples. I mean, we have worked with a lot of teams, and we see like these issues happen a lot with RPCs. And we're going to see how eRPC is going to help with all these issues. So one of the most common ones is like upstream outage. Like your primary RPC provider just goes down for 1 minute, 2 minutes, 5 minutes, even 1 day. And then, okay, what happens? Your indexing stops working, your front end doesn't show anything to the user. A DevOps person might need to get up at 3 a.m. in the morning and take out that node and kind of put another one. No zero downtime, basically. But the RPC, like, there is kind of no manual intervention needed. Like, you have automatic failover. The way it looks like in the code is, and by the way, like we tried our best to make with eRPC, you need to have like a, you can run it like with a TypeScript config or also like a YAML config. And we try to make it as less opinionated as possible. You can just tune it based on your environment. But just imagine you send the RPC request and it fails for whatever reason. Also in eRPC, we have knowledge about which errors are retriable, which errors are not retriable. It could be like a client issue. There's no point of retrying that. But imagine it's an RPC request that is actually retriable. So you have like a retry as part of a failover mechanism at the upstream level, which is your like quick node, anchor, whatever it is. And then you have like at the network level, which is Arbitrum base and mainnet. So that request comes, it fails on the upstream level, and you can configure like how many times you want to retry it. For example, here we're going to retry it for 2 times with some sort of a delay config and jitter, all those things. And imagine it also fails. Then at the network level, we're going to retry it up to 4 times. And then only if all those 4 times fail, then we're going to return the error kind of back to the user. And you can configure it based on your environment. Sometimes you have a really hostile environment, using on public nodes or like a really crazy fast chain, like hyper EVMs. You just want to like have the retry a bit more, but sometimes you want it less. So it's really dependent on your environment. This one is probably the most important slide because this is one that if it happens to you, you want to pull your hair out. And it's basically you send this request to multiple nodes and they just give you wrong results, different results. Like if get lost for this node just returns 4 logs, this one 3 logs. So what happens? Like you are going to miss events, you're going to miss transactions, and it's so subtle that you might not even know what happened until a user reports to you like, hey, why is that thing is not there? And the way eRPC helps it is like a consensus policy, right? So I'm just going to give you an example. With the consensus policy that we have, imagine you send a request to eRPC, and upstream 3, for example, is giving you a different hash in that response. So what's going to happen is like because 3 out of the 4 agreed on a result, we're going to accept that result, and then we're going to log that upstream 3 as like a misbehavior. And also you can put that misbehavior, full request responses in a like S3 or something. You can just go back and debug and understand what's going on. You can be really explicit about, how many participants you want. You might, like data quality might be really important for you. You might want to like send a single request to like 5 nodes. And if 4 out of 5 kind of agree on the result, then accept the result. What if there's a dispute, like the nodes don't agree on the result, then you might want to do certain things. You might want to return the error to the user. You might want to accept the most valid response. What if there's not like, enough participants? You might want to like do something else. And some like methods also have like some fields that are not kind of standard, so you might want to ignore them in the consensus policy. So again, you have all the kind of configs at your fingerprint to just increase the resiliency of your RPC stack based on your environment. And by the way, this config has been really useful for our, some of the customers on, fast chains like Hyper, EVM, MegaEth, because there's a lot of reliability issues on those chains when it comes to data quality. So this has been super, super helpful. Oh, by the way, I forgot, like this original idea of this was from engineer from the Circle team. We were really kind of fortunate to get, this sparked by them. Another one, which is a really common one, is slow responses, right? And it doesn't happen for other requests sometimes. Just like my debug methods are a bit slower than others. And just there's going to be, delays and the timeout on other part of your stack. So just indexing stops working. Again, users are going to have issues. And in eRPC, we have like few ways of handling this. One of them is, which we call like a hedge feature or a parallel request. So you can basically say, if a request comes and it passes more than this hard-coded amount of time, imagine like 20 milliseconds for each central for example, each get blocked by number for the real-time finality, I only tolerate up to like 10 milliseconds. If it goes more than 10 milliseconds, I'm going to send to multiple nodes. And whoever is going to give me the result fastest, I'm going to accept that. I'm going to cancel all the others. So that's just going to, again, increase like the speed of your RPC stack. And for example, this quantile-based feature that we added was really, really useful because sometimes you want to adapt based on different situations. You don't want to hardcode a certain waiting time. So, okay, if this request is slower than P95 latency of all the other methods, then I'm going to basically start a hedging mechanism. So that just helps a lot with reducing the latency of your RPC request. And this one is probably like the only slide that is not part of the eRPC open source core. It's what we call an edge node, and that's like one of our premium features. It kind of combines your RPC nodes. You can have your RPC nodes from different providers. You can bring it to us, and we kind of have an edge node service. These kind of get combined together. It can be even deployed to your own infra stack for just the lowest possible latency. And with that, this edge node is like kind of a proactive indexer that is on tip of the chain. Imagine like for the last 10,000 blocks. And it gets like the raw data and it can reconstruct like lookup methods like get block by number, get logs, and all those things. So, and also it does like data integrity checks as well. And the effect you see basically on the results is that like you're going to see like under 10 millisecond RPC responses after you kind of enable this node. And whatever RPC methods it cannot handle through the edge node, it's going to basically handle through your backup RPC providers. So you just get like a benefit of both worlds. So if it's interesting to you, just come talk to me or contact me through our Telegram and a website. All right, so this one is also a really, really important one. ETH get logs. A lot of different application developers we talk to, they have issues with different providers because, again, different providers have different log ranges, right? And then you need to manually intervene and do something on the client side because not all of them are, let's say, standard. But with eRPC, we do like auto log splitting, kind of automatically, so it kind of you don't need to worry about it as a developer. And the way it works is, by the way, you can also define like a max allowed range in the eRPC config. So you just don't want to stop the abuse of your, let's say, eRPC instance. But imagine like you send a like 20K block range, it gets logs. And okay, is it less than that 30K that I define? Yes, it is. Then, for example, my node 1 or node 2 only support like a 10K range. So that request is going to be split in like 2, like 10K, 10K. And then we're going to like merge the results and give you the responses. And also there's data integrity checks and all those things. So the order of the response is not going to be basically have issues. So that also helps with the the get logs, which is a kind of a pain for a lot of application developers. All right, Last but not least, I think this one is the one that I'm really proud of about eRPC because it just makes it way more than a dumb LV solution, because for literally every upstream RPC you have in your stack, you want to dynamically track how it's like performing, right? It's not like a traditional elbow, like you overwhelm a node too much, and actually because of that overwhelm, the node isn't going to go down, and then you go to another node. You want to dynamically always track like how is this node doing in terms of multiple characteristics. You just don't want to do like a simple round robin. And eRPC kind of lets you do that on like different dimensions, and it's up to you as a developer to understand your environment and see like how do you want to define this. So for example, imagine you're building like a DeFi app, and for the real time, you want to punish the nodes that are lagging behind the tip of the chain. So for example, you want to give them like a 20 score in the scoring mechanism, but you don't care too much about the error rate, like the blockhead lag is the most important thing. But for the finalized data, maybe you want to actually punish a node if they are having a large latency, right? So ultimately, like these different dimensions is gonna result in a score, and based on that score, like the nodes that basically have the highest score, they're gonna get majority of the requests, and the nodes that are like constantly failing, constantly behind the tip of the chain, I mean, they're gonna still be tried because a node could have like a transient issue, so you might want to still like try them. But again, like this helps a lot by keeping your RPC stack healthy and make sure that not a single node gets overwhelmed. I think I can skip this part. Yeah, these were just some of the examples of how eRPC is helping with different cases. Probably if you go to our GitHub, probably like hundreds of these different cases that we are handling. But yeah, please check our GitHub, join our Telegram. There's like really smart people that are having interesting conversations there. And thank you.
Kasra, what an excellent presentation there. We do have time for just one question here. And the question is with, well, actually a couple of questions here now I see here. The first question is, what's the happy path latency overhead of using eRPC?
Oh, that's a really good question. So we have optimized this a lot in the past year, but you can expect like some added latency, maybe 5 millisecond or 10 millisecond. But again, based on the environment, if you care more about data quality, that kind of latency can be also added more because you're checking against like multiple nodes. But if you mostly care about latency, there are ways of making it like really, really minimal, basically.
Okay, perfect. And last question I see here, it says, with so many config options and use cases, do you have examples of optimized configs for different use cases?
Excellent question. We have eRPC, basically, if you start running it, there's a lot of sane defaults already in there, so you don't need to like worry about it. We have some good stuff in the docs. Also, if you join Telegram, you can ask us about your environment. But because it's like really different about different use cases, I think you need to talk to us probably to optimize for those things. But again, the code itself has some defaults, the docs has some good examples, and you can talk to us if there's any questions.
Excellent. Well, please, a round of applause for Kasra.